Last week we spent time talking about electromagnetic radiation, and we focused on how it's created at the sun, and then also how it interacts with the Earth's surface features. But we haven't yet talked about what happens in between those two. And it turns out that the interactions with the Earth's atmosphere have a significant impact on the amount and type of electromagnetic radiation that's ultimately received at our sensors, so what we're ultimately recording and looking at. So we're going to spend a little bit of time talking about these atmospheric interferences. But first, let's take a step back. I found a great little video that reviews this whole process.
Let's start with some ground surface features. I'm going to use the sun as our source of electromagnetic radiation. We then bring in our eye in the sky, a sensor on either a satellite or airborne platform. From the sun, we start with all the irradiance or energy that's available at the top of the atmosphere. Irradiance is a term that refers to energy at all angles or directions. Some of this energy radiates down to the surface of the Earth, which will then bounce off individual features and eventually reach the sensor to be recorded as radiance. Radiance has a specific angular component. Considering the energy that is emitted from the sun, not all of it actually reaches the ground. Some is scattered within the atmosphere. Some of this scattered light can then also reach the ground. Therefore, the total irradiance reaching the ground is the sum of that which directly hits it, plus the additional indirect source. Now, some of that energy is scattered within the atmosphere.
We'll stop Karen Joyce right there, because what we want to talk about today is what happens in the atmosphere to this electromagnetic radiation. And that's going to help us figure out how we can adjust what the total radiance is received at the sensor based on what we know is happening within the atmosphere. So this moves beyond just a theoretical understanding. We're going to need this to apply these principles so that we can adjust what we receive at the sensor, this at-sensor radiance, so that it better matches the true reflectance, the at-surface reflectance that was given off by the Earth's surface features. There are two primary interactions that occur between electromagnetic radiation and the Earth's atmosphere. One of those is simply scattering, so this incoming sunlight would hit air molecules or other particles in the atmosphere and bounce off in all directions. And then there's also absorption, so these molecules in our atmosphere also interact with the electromagnetic radiation just like surface features do. They can have that radiation be reflected, be transmitted, or be absorbed. And so there are many particles within our atmosphere that will absorb particular wavelengths. We'll deal with each of these interactions individually and start with scattering here. So when we're talking about scattering, we're essentially saying that electromagnetic radiation comes in and it hits some object and it bounces off in some unpredictable direction, often in many directions. How light is scattered in the atmosphere really depends on a couple of different things. First of all, the size of the particles that are present in the atmosphere, and that makes sense because the larger your particles, say for example a big dust blob, the more photons will hit that and thus the more scattering there'll be. But it also depends upon which wavelength you're talking about within the electromagnetic spectrum. Shorter wavelengths tend to come into contact with more particles, and therefore there's much more scattering in those shorter wavelengths like the blue wavelengths compared to the reds or the infrareds. The path length also makes sense because if you think about it, the longer the path of atmosphere that light has to travel through, the more likely it is to come into contact with particles or molecules. So the longer that path length, the more scattering you're going to have. And then also the density of those atmospheric particles. So not just the size of the particles, but also how many of them you have. So because all scattering is not created equal based on those four different variables, the scientific community has essentially divided up scatter into three major types. And the first type we'll talk about is called Rayleigh scatter. Rayleigh scattering is sometimes called molecular scattering because it only occurs with very small particles. And when I say small, I'm talking about on the order of magnitude of the wavelengths themselves. So these molecules, these particles, are so tiny that the larger wavelengths would just zoom right around them and not interact at all. It's really only the smaller wavelengths that are impacted by these very small molecules. And so because of that, Rayleigh scatter is selective scatter, meaning that the shorter the wavelength, the more scatter there is. And eventually, as you get out into the infrared, you have almost no Rayleigh scattering anymore because those wavelengths are long enough that, again, they just travel right around those molecules. To give you some perspective as to how much that difference can be, just going from the blue to the red wavelengths, right, we're only talking about, say, 200 nanometers here, you have 4 times more scatter within those blue wavelengths. And this is important to keep in mind with remote sensing because we have to remember that our blue bands are going to be much more impacted by the atmosphere than our reds and our infrareds. I'm sure at least half of you can think back to your high school science class sometime when they asked you to explain why the sky was blue. And if only you had known then that all you had to do was write Rayleigh scattering, you could have saved yourself a whole paragraph of explanation. But essentially that's what's happening because those shorter wavelengths are scattered more readily in the atmosphere by those smaller molecules that dominate the atmospheric composition. That means they scatter more of that blue light, and that's what we end up seeing. The longer wavelengths, the greens and the reds, tend to pass right through. So this is why the sky is blue. But of course there's always some smart aleck who says, well, the sky isn't blue, the sky is sort of white. Well, that certainly is the case when you don't have a clean atmosphere, and instead of just having those small molecules, instead you have other slightly larger particles in the atmosphere as well. And that's a perfect segue into our next type of scatter. And that's a perfect segue into the next type of scattering, which is called Mie scatter. And this is when we have particles that are a little bit larger. Typically, you're going to see Mie scatter when the size of the particle matches the size of the wavelength. So again, this is another selective scattering mechanism. Only those wavelengths that are approximately the same size as the particles themselves are going to be scattered. But this is very common when you have dust or water vapor in the atmosphere, pollution, smoke. All of these things are about the same size as many of the visible wavelengths. In terms of remote sensing, what this tells us is that when we do have high humidity days or high pollution days, we know that it's not only going to be those shorter blue bands that are going to be scattered, but now we have to also start thinking about our green and our red bands as well that are going to be impacted by the Mie scatter. So as an example, back to another common high school science question, why are sunsets red? Again, you could have just answered Mie scattering, because essentially what happens as the sun starts to sink down towards the horizon is that those rays of sunlight, to get to you, now have to pass through much more atmosphere before they reach your eyes. So imagine you're standing over here, and here's the sun all the way down on the horizon. And so as that electromagnetic radiation is passing through more and more atmosphere, those shorter wavelengths are scattered a lot more than the longer wavelengths. So very early on, you've lost most of your blue light, right, as it's traveling through this atmosphere. A little bit closer to you, you start to exhaust your green wavelengths, and what you're left with, what reaches you finally, are just those red wavelengths. And this is what you end up seeing, a sky that appears red because there's so much atmosphere. And as the light is traveling through this atmosphere, it's encountering much more of these larger particles, which may not be as common, but when you're passing through all of this atmosphere, you're going to be hitting those. So now your longer wavelengths, like your reds, are being scattered more readily, plus you've already lost your blues and most of your greens. So you end up with either an orange or a red looking sunset. The final class of scatter is called non-selective scatter, and essentially this is when you have particles in the atmosphere that are so large that just about all of the wavelengths hit them. Now, this might not apply to radio waves or microwaves because we know that the radio can still go through very large particled masses like clouds, but it certainly affects the wavelengths that we're typically looking at with our satellite remote sensing. And this is just because these particles are so large that all of these wavelengths, there's no way for them to wave their way around them. They're all going to hit these particles and be scattered in all directions. And this is particularly common when you don't have water vapor, but water droplets that have condensed in clouds. Larger particles like dust or very heavy smoke will scatter in all wavelengths. And this is why clouds are sort of the bane of our existence, because really if you have water droplets in the atmosphere, there's going to be very little that you can do to see anything below them unless you're in those much longer wavelengths. So to summarize, one of those interactions that we know occurs in the atmosphere is the scattering of electromagnetic radiation. And how that light is scattered depends upon both which wavelengths of light you're talking about, as well as the size and density of the molecules and particles that are in the atmosphere. And then also don't forget the fourth category, which is just how much atmosphere that light has to pass through. The other major process of atmospheric interference is absorption. Absorption is different from scatter because when light is scattered, the wavelength and the inherent energy of that photon doesn't change. But when light is absorbed, it actually changes the wavelength by essentially absorbing a portion of that energy contained within that photon and then either reflecting, refracting, or scattering the rest of that energy. If you were to break this down into component pieces, the scattering that we were talking about before takes up about roughly 9% of that total solar irradiance that comes towards the Earth. But another 19% is actually absorbed by the atmosphere. Consider that another 23% is just reflected straight back out of the atmosphere by clouds, and you're only left with about half of the solar irradiance available hitting the Earth's surface. That just provides a little perspective of how much interaction there is between electromagnetic radiation and the Earth's atmosphere. But just like scattering and how variable that can be, absorption is not the same across all wavelengths either. So really what we end up seeing is that all of this continuous spectrum of light that comes from the sun, what actually reaches the surface is only certain wavelengths because our atmosphere is so effective at absorbing other wavelengths. And this is a good thing and part of what makes life on Earth possible. When we talk about these regions where there's not a lot of atmospheric absorption, we refer to these as atmospheric windows because essentially they're our remote sensing windows to be able to see the surface. While there are lots of different molecules that can absorb radiation, there are four primary molecules that do most of that work. One of those is nitrous oxide. We know that nitrogen is the most common element in the atmosphere. We also have absorption by oxygen and then also ozone, and it's the ozone that is really responsible for absorbing most of these very short wavelengths, these damaging gamma rays and X-rays. Carbon dioxide is another strong absorber in several wavelengths, and then water really takes up a bulk of what's absorbed across our visible near-infrared thermal wavelengths, not as much in those shorter, more powerful wavelengths. So taken as a sum, right, if you were to basically think of the combined effect of all of these different molecules, this is what we end up seeing at the surface of the Earth. So at the top of the atmosphere, you would expect all of this to be white, right? Because essentially what's this y-axis is how much of the light is absorbed, right? So if you have white, it means that there's nothing absorbed. At the top of the atmosphere, there's nothing to absorb it. So you would expect this whole graph across all of these wavelengths to just be white. But because of this absorption by the atmospheric particles, we end up really not getting any of these wavelengths that are now represented in the dark reaching the surface of the Earth. In terms of remote sensing, why do we care about this? Well, it's pretty straightforward. If we can't see it, then we don't get any signal to interpret. So most sensors are actually designed to take advantage of those atmospheric windows. So even though you may have a field spectrometer and know that a certain wavelength is really important for identifying a particular feature that you're interested in, if it's not something that can make it back through the atmosphere and reach your sensor, then it's useless to you. So sensors have to be designed with that caveat that the bands that they're built with must be within atmospheric windows, right? These windows where we know the light can pass down through the atmosphere to the surface and reflect back up to the sensor. I'm going to try not to confuse you here because what we're looking at now is a graph that's basically the inverse of what we were looking at before. So on the y-axis, now instead of seeing how much light is absorbed, we're seeing how much light is actually transmitted. So according to this graph, the atmospheric windows are actually those locations that have the highest transmission values. And if you look up here at where the Landsat bands are located, you'll notice that each of those is located in regions of very high atmospheric transmission. They purposely avoid these other regions that are blocked. So for example, look at band 5. Band 5, the width of it and its location is very strategically placed in this narrow zone where electromagnetic radiation can still penetrate the atmosphere. It's the same with band 7 out here, right? They placed that pretty strategically. And then again for band 6. And if you had to summarize essentially the overall impact of all this absorption, what essentially you could say is that we're reducing the quantity overall, because all wavelengths will scatter and absorb a little bit, right? But definitely stronger in some regions for certain wavelengths. But overall, we're seeing a reduction in the energy reaching the Earth and an almost complete reduction in certain wavelengths. And this is kind of a fun figure to look at. What this dotted line shows us is the actual amount of solar irradiance that hits the top of the Earth's atmosphere. So this is the light that is reaching the Earth after it travels through space. But what you see in the darker line is what we actually receive at the Earth's surface. And so we're seeing the effect of scatter. So we've lost a lot of that energy to scattering in these visible and the near-infrared wavelengths. And we've lost a lot of these other regions due to absorption. So these sort of deep wells, those are absorption features. Water, CO2, our oxygen. We see these shorter wavelengths, which aren't even on the graph, absorbed by ozone. So the overall impact is a reduction in the energy that's reaching the Earth, and we call this atmospheric attenuation. While this might be good for life on Earth, I personally wouldn't want to be inundated by X-rays or by ultraviolet radiation, but it's not necessarily the best thing from a remote sensing perspective because we're essentially losing signal, right? We're losing potential energy that we could then use to find out about the Earth's surface. So let's think about what we know in terms of atmospheric interference and what determines how much atmospheric interference there is and which of these things we can control. We know that inherently longer wavelengths have lower energy associated with them. Those are just the laws of physics. There's nothing that we can do about that. We also know that how much electromagnetic radiation is scattered and how much is absorbed is dependent upon, again, which wavelengths we're talking about and what particles and molecules are in the atmosphere. We can't control either of those either. But what we can control sometimes is the path length. We can try to acquire imagery when the distance between the sun and the surface and the sensor and the surface is shortest. So we're minimizing how much atmosphere the light has to pass through. One of the ways we can do that is by choosing to use sensors on aircraft instead of on satellites. So an airborne sensor is always going to be flown at a lower altitude than a satellite, and therefore you may be able to cut off part of the atmosphere between the sensor, at least, and the surface. If possible, we can also choose to acquire imagery during the season when we know the sun is highest in the sky, right? So when the sun is low on the horizon, it has to pass through much more atmosphere before it reaches the surface. It's also helpful to be closest to the equator because that's where the sun's rays most directly strike, but you can't often choose exactly where you are interested in studying. But one other variable that you can sometimes control is the time of day that you're acquiring your imagery. So anytime the sun is lower in the horizon, be that because of the season or because of the time of day, the light has to pass through the atmosphere at an angle, which makes for a longer path. So you always want to try to acquire your imagery closest to what we call solar noon. So solar noon means for any given day, at what time is the sun highest in the sky. And what's really interesting is it isn't always noon. Solar noon is often a little bit after noontime, but again, it depends on the season, and there are really great calculators. You can go online to look up what time solar noon is for your latitude and longitude and for your given date. The other option we have is to avoid any days where we know we have more of those particles that would result in higher scattering or higher absorption. So for example, we might not want to use imagery from days that we know had very high humidity or that had a large percentage of clouds or fog, or even atmospheric pollution. If you have days where you know you have a lot of particles in the atmosphere, you're going to have a whole lot of atmospheric attenuation. So for satellites, you may say, okay, I can't use that date, and you would look for another date that had better atmospheric conditions. With airborne platforms, you have a little bit more flexibility, and in fact, most of the contracts that we write to get vendors to collect airborne imagery for us will have very specific qualifications for what the conditions must be like before they fly. So in other words, we're not going to pay them to fly on a day that looks like this, because that imagery would be almost useless to us. And similarly, we also write into these contracts specifications for the time of day the imagery can be collected. There are some vendors who see a clear day with no clouds and want to gather as much imagery as they can and fly as long as they can. But if that means they're starting at 9 in the morning when the sun is way down here, not only are you going to have issues of atmospheric interference, you're going to have tremendous shadows in there as well. And so we'll often put a window, a data acquisition window around the solar noon, usually plus or minus 2 hours of solar noon, so they have no more than 4 hours on a given day that they can collect imagery for us. Once you've exhausted all of these options for how to limit the impact of the atmosphere on your electromagnetic radiation and the signal your sensor receives, your next step is to try to correct for this atmospheric attenuation. And there are lots of different ways to do this. Some are very simple and straightforward, and some are actually quite complex and also expensive. So we are going to spend another lecture talking about atmospheric corrections and a whole lab on that as well. Essentially, what all these different techniques are attempting to do is to take this original radiance that reaches the sensor, so this would be the continuous spectrum for what that looks like, and then either based on some surface features of known reflectance curves or based on these physical models where you actually model what the atmosphere is doing based on known physical properties, you're converting that raw radiance into a reflectance value which approximates what that spectral curve would look like if the sensor were located right at the surface and the atmosphere had not been wreaking havoc with your signal. So after all of this talk about how horrible the atmosphere is in terms of remote sensing applications, the knee-jerk reaction is to think, oh my gosh, I have to do an atmospheric correction. What do I do? But the reality is you don't always have to do an atmospheric correction. It depends on your application. So for example, if all you're interested in doing is looking at imagery and making pretty pictures, and often this is the case, there's no need to do an atmospheric correction. It's okay if some of these bands are scattered a little more than others. I can guarantee that Google Earth is not running an atmospheric correction on any of its imagery that's up on the web. It's simply looking for cloud-free images and using those. Also, it might not be necessary if you're just trying to differentiate between really obvious features. Water is going to look different from vegetation whether you've applied an atmospheric correction first or not. They're just so drastically different that even with scatter and with absorption of the atmosphere, they're not going to look that different. It also isn't necessary if you're going to be running classifications based on these object-based methods. This is really an interesting approach that uses those photo interpretation techniques we talked about earlier in the class, but it actually trains the computer to do those. So in that type of an analysis, you're not basing it solely on the actual spectra and on the reflectance, so it doesn't become as important to make sure that's perfect. Instead, that object-based feature extraction is also incorporating characteristics of shape or size or texture or contrast. And so when you're bringing in all of those additional characteristics, it isn't always essential to get the spectra perfectly corrected. But pretty much for any other applications, when you actually are interested in spectral values, in particular if you're trying to compare images either across location or over different image dates, you have to make sure you're comparing apples to apples. So you definitely would have to do an atmospheric correction if you were looking at more than one image. And then you also would need to do this anytime you're trying to compare the spectra you've collected to known reflectance properties, which are often stored in these spectral libraries. So all over the world there are these databases that store spectra of what different surface materials look like, and often those are used to train imagery. So say for example, you were looking for a very particular mineral, you could go to one of these spectral libraries and download what its pure spectra looks like, and these are always acquired with a handheld spectrometer where there is no atmospheric interference, and you would want to compare that to the spectra in your imagery. But in order to do that, again, to compare apples to apples, you would have to make sure you've done an atmospheric correction first. Pretty much all remote sensing software packages have some variety of atmospheric correction modules. But ENVI in particular, I think, has quite a few, and some of these are pretty straightforward, and we will practice some of these in lab. Other modules, notice the little $sign, are great. These are the more theoretical models, very complex, that try to actually look at the physical properties of constituents in the atmosphere and how that would interact with light at different wavelengths, and you have to enter all of these parameters about what the weather conditions were, what the visibility was like, what the humidity was, all of these different things, and then these modules will run, but they're pretty expensive to buy. They don't come with ENVI automatically. They're add-ons, and we don't have licenses for these in our labs. But no matter which, either these sort of more simplistic, easily available tools or the more expensive ones, no matter which you use, you still have to do some pre-processing before you get into that atmospheric correction. And we'll talk about some of these when we get into our lab on pre-processing. So I think we'll end it there for this week, and hopefully now you are comfortable and well versed in talking about electromagnetic radiation and what we need to know in order to do remote sensing. You've made it through one more remote sensing video. Nice work, everybody. Until next week.